Okay, two universal line charges are located in free space at x equals 0, y equals plus or minus 0.4 meters. What force does each line exert on each other? So, first thing is, this is, I wrote some notes over here. This is essentially a 2D problem because x is this is for x equals 0 on the x equals 0 plane. So this is our y and z. So since you have these two lines, actually let me use a different color. You have two lines coming at each other. Get out of here. Like this and like this. They're not going to have any component of x because they're on the same plane of x. So there's no way they could like influence each other in the x direction, if that makes any sense. They're only going to have influence in the y direction, because even in the z, if you look, since they're equal in size, because they're identical, each component of z is going to cancel. So this one's going to push on this one like that. This line's going to push on this line like that, and this line's going to push on this line like that. Right? So really, you only have we know we're going to have one component of force, and it's going to be in the y direction, and it's not going to be in the x, not going to be in the z. So let's break that down even a little more. Actually, I'll do it up here. Let me make the lines a little big just so I can make chunks. So if we want to find out the force per unit length that each line charge exerts on each other, we need to break it up into segments because we're going to have to do an integral to solve this problem. So, actually I'll do this one too. Break this up into segments. And this is at 0.4 meters. 0.4 meters. So let's look at this section right here. We'll call this, we want to find df, right? And df is going to be influenced by all these charges coming at them in this direction. You see what I'm saying? Like the whole entire line is going to be placing force on this one little component, and then we're going to need to integrate over this whole line, doing the integral just like that for each one. So it's this one's gonna have look like that, and then down here you're gonna have this one. So we need to find a way. We basically need to find a way to define df. Well, we know F equals QE, right? So df would equal dQE, and that's because if Q is the charge of like a whole object, dQ would be the smaller charge. So like this would also have like some dQ component, right? So there you go. You have df in terms of dQE, but we don't really have. We have our lines in terms of rho L. So now we need to change dQE to some sort of rho L and Z. So how would you do that? So dQ is dQ is in terms of coulombs, right? And rho L is coulombs per meter. And we can evaluate and say dQ is equal to rho L times dz. And the reason that works out is because rho L is coulombs per meter, and dz is a meter. Boom. Coulombs. Your units work out. Everything's good. So now you have dq is rho L dz. So now, if you punch that into here, you have df equals rho L. Let me put the e first. Rho L e dz. See what I did? All I did is I punched these two equations in. So the reason this is important is because now we have the thing we want, df, in terms of things we have, like rho L and z. Because we know z is going to be, well, that's another thing. I didn't really talk about that yet. So it wants force per unit length. So unit length, in this case, is a meter. So it wants force of 1 meter, right? So now that we have this perfect little equation, we can do the integral of df equal to the integral of rho L e dz, and we can do that from 0 to 1. From 0 to 1. And that gives us a value of force per 1 meter. So now we have to find out what this E value is, which we already have that in terms of our equation. That would just be like this. Rho L over 2 pi epsilon naught r. And we don't have to worry about any unit vector or anything like that because this is a 2D problem essentially. So unit vectors are not necessary. So this will just be f. We'll just call this f. It really kind of be 1 here, but we'll just call it f because we're talking about force. It's a little tricky because like technically you wouldn't want to say force is Newton's meter because force is really a Newton, right? But right now I'm just going to call this f, and then we'll evaluate this integral, and that'll give us our answer in newtons per meter, which is what we want. So integral 0 to 1 of rho L squared. I'm just plugging in this E value here. 2 pi epsilon naught. Now we don't know what our R is, but wait, oh yeah, we do, because it's the distance between the two lines. So 0.4 and then another 0.4. That's 0.8. And then dc. So we know everything in this problem now. We know rho L is rho L is what, 75? Yep, 75 Newton. So F is equal to you'd plug this in and then evaluate the integral. And then you would get F is equal to 126 micronewtons per meter. And then if you want to be more accurate, because again, like I was talking about, the force is really in terms of unit, in terms of newtons, not newtons per meter. So you'd say F of 1 meter line equal to 126 newtons. And then that's your answer. So that gave you this one right here because it's positive. And like we were saying, these are going to be equal opposite forces because they're the same line. So the other F will be call this plus 0.4, and then we'll call this minus 0.4. That would be equal to, oh, and this is in terms of y. And yeah, these are all in terms. This is all in terms of y. We talked about that already because we know that it's going to be in the y direction and only in the y direction. So there you go. Peace.